Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is three-phase transformers. Our objective is to examine three-phase transformers, electrical devices used to step up, step down, isolate, change the electrical configuration, and phase shift three-phase AC voltage. We'll additionally learn to interpret standard three-phase transformer nomenclature and simplified connection and displacement diagrams. This lecture operates under the presumption the viewer has more than a passing familiarity with single-phase transformers and three-phase AC, as illustrated in the Introduction to Transformers and Introduction to Three-Phase AC lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. In a perfect world, I could just tell you to go watch the Introduction to Transformer lectures 3 times, seated at 3 different angles, and call it good. But I can't, because there are some peculiarities about three-phase AC transformers that I need to discuss, especially when it comes to connection diagrams. This being said, for the most part, everything I said in the previous lecture on single-phase transformers remains true. You'll recall a transformer is an electrical device used to step up, step down, and isolate primary and secondary voltage via electromagnetic induction. As you are no doubt aware, if a transformer has 1 turn in the primary for every 2 turns in the secondary, voltage at the secondary will be stepped up such that it has twice the voltage of the primary. Consider 3 independent 1 to 2 step-up single-phase transformers, each being fed 1 line-to-neutral phase of a light industrial 120-volt line-to-neutral, 208-volt line-to-line 3-phase AC system. 120 volts at 0 degrees, 120 volts at negative 120 degrees, and 120 volts at 120 degrees. The secondary outputs would understandably be twice the primary input, yielding 240 volts at an angle of 0 degrees, 240 volts at an angle of negative 120 degrees, and 240 volts at positive 120 degrees. Conversely, if a transformer has 2 turns of the primary for every 1 turn in the secondary, voltage of the secondary will be stepped down such that it will have half the voltage of the primary. Consider 3 independent 2-to-1 step-down single-phase transformers, each being fed 1 line-to-neutral phase of light industrial 120 volts line-to-neutral, 208-volt line-to-line 60 Hz 3-phase AC system. 120 volts at 0 degrees, 120 volts at negative 120 degrees, and 120 volts at positive 120 degrees. The secondary outputs would understandably be half the primary inputs, yielding 60 volts at 0 degrees, 60 volts at negative 120 degrees, and 60 volts at positive 120 degrees. You will note that each secondary, regardless of step-up or step-down configuration, does not induce any phase shift between it and the primary. Secondary output of transformer 1 remains at 0 degrees, secondary output of transformer 2 remains at negative 120 degrees, and secondary output of transformer 3 remains at positive 120 degrees. In summary, the winding-to-winding magnetic transfer power does not influence phase shift in any way, shape, or form. This fact will remain true for our later discussion of three-phase transformers, although, as you'll soon see, how you configure the primary and secondary windings can and does influence phase shift when considered as a whole. Of critical importance for today's discussion on three-phase AC transformers is the location of the phase dots. You'll recall from our previous discussion on transformers, the ends of the winding with the phase dots simultaneously peak and valley. If we were to hook up an AC voltmeter positive to negative across the primary dotted end to non-dotted end, and another AC voltmeter positive to negative across the secondary winding dotted end to non-dotted end, and overlaid a plot of instantaneous voltages, we would see the secondary output perfectly in phase with the primary input. If, however, the phase dots were on opposite ends of the secondary winding, effectively using the secondary output backwards or inverted, we could see that the secondary output is perfectly out of phase with the primary input, exhibiting a plus or minus 180 degree shift, such that the secondary output valleys when the primary input peaks, and peaks when the primary input valleys. Given your previous experience with single-phase AC transformers, these observations about turns ratio and phase dots should be trivial in nature. This being said, up to this point, we're acting as if we're dealing with 3 isolated independent systems and haven't hooked them up in any fashion. Since what we're about to get into can get real confusing real quick, let's ditch the step-up and step-down nature of the transformers and just use 1-to-1 isolation transformers. This way we can concentrate some of the cool phase shift properties we're about to observe without getting lost in details about changes in magnitude. Consider 3 independent single-phase transformers with a 1-to-1 turns ratio, each being fed 1 line-to-neutral phase of a light industrial 120-volt line-to-neutral, 208-volt line-to-line 60 Hz 3-phase AC system. 120 volts at 0 degrees, 120 volts at negative 120 degrees, and 100 volts at 120 degrees. The secondary outputs would understandably be the same magnitude, yielding 120 volts at an angle of 0 degrees, 120 volts at an angle of negative 120 degrees, and 120 volts at positive 120 degrees. Given the 1-to-1 turns ratio, output remains the same magnitude as input. However, let's continue to call the primary input the high voltage side and the secondary output the low voltage side, since it's critical to a later discussion on naming conventions. Now, rather than treating these as three independent systems, let's hook them together. Consider just one of many possible configurations. Since we're feeding each primary line to neutral voltages, one way of arranging the three primary windings is to conjoin each primary winding non-dotted end as the neutral connected central node of a Y configuration. Similarly, one could conjoin the three secondary windings non-dotted ends to form another neutral connected central node of another Y configuration. As one might expect, if each of these now interconnected 1-to-1 transformers were being fed one line to neutral phase of a light industrial three-phase AC system, the secondary outputs would understandably be the same magnitude, yielding 120 volts at 0 degrees, 120 volts at negative 120 degrees, and 120 volts at positive 120 degrees. This being said, since we're illustrating each transformer as an individual entity, this diagram might be a little confusing given the overlapping wires. It doesn't clearly illustrate the Y with neutral shape we're going for. For this reason, we might just draw a Y-configured high-voltage primary and low-voltage secondary as such, with the understanding high-voltage primary winding capital A maps to low-voltage secondary winding lowercase a, high-voltage primary winding capital B maps to low-voltage secondary winding lowercase b, and high-voltage primary winding capital C maps to low-voltage secondary winding lowercase c. One can clearly visualize the Y shape with neutral now. As aesthetically pleasing as these diagrams may be, they're somewhat cumbersome to illustrate. For this reason, three-phase AC transformers customarily employ what's known as a simplified connection diagram, which looks something like this. Rather than illustrating each winding as a coil, each winding is instead illustrated as a rectangle with a phase dot, clearly indicating which end experiences simultaneous polarity shifts. Additionally, rather than tilting that at eye-pleasing 120-degree angles, the windings are drawn parallel to each other. Imagine bending high-voltage primary winding capital A and tilting it till it reaches the horizontal. The same thing for high-voltage primary windings capital B and capital C. And the central neutral node is a fourth connection that's brought out to the input side. Similarly, imagine grabbing low-voltage secondary winding lowercase a and tilting it till it reaches the horizontal. Same thing for low-voltage secondary windings lowercase b and c. And again, the central neutral node is a fourth connection brought out to the output side. High voltage primary winding capital A still maps to low voltage secondary winding lowercase a, B to B, and C to C with no phase shift. Using the simplified connection diagram gets the same point across using far less space and unnecessary complication. You may also see simplified connection diagrams using terminal numbers, capital A1 and A2 for the ends of primary high voltage winding capital A, and lowercase a1 and a2 for the ends of secondary low voltage winding lowercase a. Similar terminal numbers may also be used for the high voltage and low voltage B and C windings. I find these numbers clutter up the diagrams a little much, so I typically just use the capital and lowercase letters, and importantly, clearly indicate which end of a particular winding has or does not have a phase dot. Given this arrangement of primary and secondary windings, consider the phase shift of the low voltage secondary output with respect to the high voltage primary input. Given light industrial 120 volt line to neutral, 208 volt line to line, 60 Hz three-phase AC, phase 1 primary input is 120 volts at an angle of 0 degrees, and employing a transformer with a 1-to-1 turns ratio results in low voltage phase 1 secondary output of 120 volts at an angle of 0 degrees. Similarly, low voltage phase 2 output yields 120 volts at an angle of negative 120 degrees, and finally low voltage phase 3 output yields 120 volts at an angle of 120 degrees. If we were to draw the phasor diagram for the high voltage input and the low voltage output, they'd be perfect copies of one another. Outputs are in phase with inputs. Configured in this essentially identical manner, this bank of transformers results in no phase shift between the Y-configured high voltage primary input and similarly Y-configured low voltage secondary outputs. For this reason, this configuration might be referred to as a YN-0 three-phase AC transformer because the high voltage side is a Y with a neutral. The low voltage side is also a Y with a neutral, and the low voltage secondary output is perfectly in phase with a high voltage primary input with 0 degree phase shift. We'll take a look at the details of transformer naming conventions in a moment. Given the numerous terminals available on a three-phase transformer, a YN-YN0 configuration is just one of many possible configurations. Consider this subtle modification and its important consequences. Rather than tying together the non-dotted ends of the low-voltage secondary windings, let's instead tie together the dotted ends and use them as the central node of a Y-configured output, effectively using each low-voltage secondary winding backwards or inverted. Used in this fashion, the low-voltage secondary outputs of each transformer will be perfectly out of phase with the high-voltage primary inputs or exhibit a respective plus or minus 180-degree phase shift. When the input peaks, the outputs valley. When the inputs valley, the outputs peak. Long story short, if you're using the secondary backwards, add or subtract 180 degrees from each phase. If high voltage phase 1 primary input is 120 volts at an angle of 0 degrees, low voltage secondary output 1 would be 120 volts plus or minus 180 degrees. If high voltage phase 2 primary input is 120 volts at an angle of negative 120 degrees, low voltage secondary output 2 would be 120 volts at an angle of negative 120 degrees plus 180, or 120 volts at 60 degrees. Similarly, if high voltage phase 3 primary input is 120 volts at positive 120 degrees, low voltage secondary output 3 would be 120 volts at an angle of 120 minus 180, or 120 volts at an angle of negative 60 degrees. If we were to draw the phasor diagram for the high voltage input and low voltage output, each phasor would be the polar opposite of one another, pointing left when they were pointing right, pointing up when they were pointing down, pointing in when they were pointing out. You get my point. Totally opposite. Given the low voltage outputs exhibit a 180 degrees shift with respect to the high voltage inputs, you'd think they call this a YN 180, but they don't. They call it a YN 6, where 6 means 180 using what is known as clock notation. Like I said, this can get real confusing real quick, so it's probably a good time to introduce clock notation and explain standard three-phase transformer naming conventions. Now, because this is an accepted standard that the whole world should use, it doesn't mean everybody does, so be prepared for variations in this theme and straight up incorrect applications of it. Long story short, trust no one, including me, especially me. Always verify the connection diagrams for your specific transformer of interest directly from the manufacturer. The generally accepted three-phase transformer naming convention uses 3 parts. Part 1 is the configuration of the high voltage side, Y or delta using capital letters Y or D. Note the dumbest D students in the most broken school systems in the most backward state, Mississippi, I'm looking at you, sometimes call Y configurations star configurations, like a really lame star with only 3 arms. Do not use the term star. It is a Y. It will always be a Y. It is not a star. It will never be a star. Stop trying to make star happen. Anyways, part 2 is the configuration of the low voltage side. Y or delta using lowercase letters, Y or D. Similar prohibitions exist on using the loser term star for clearly Y-connected low voltage windings. Additionally, if the high voltage or low voltage side, when configured as a Y, not a star, has a fourth neutral line, it'll indicate it with an N. Again, capital letters for the high voltage side and lowercase letters for the low voltage side. Additionally, you might run across a Z or a zigzag connection, which I'll explain later, or maybe not at all. Finally, part 3 is the phase shift of the low voltage side with respect to the high voltage side using clock notation. Again, low voltage with respect to the high voltage. Does the low voltage lead or lag the high voltage? The high voltage is the reference. This has important ramifications we'll explore in later example applications. Clock notation necessitates you know how old school analog clocks work. If you've never seen one before, get your grandma to take you to church or bingo or whatever old people do all day, and I'm certain you'll run into one. Anyways, clock notation illustrates the high voltage side, using one hand pointed straight up and down at 12 o'clock. After all, it's the reference. And then the low voltage side has another hand that leads or lags it given anti-clockwise rotation. Yeah, you heard me right. Despite using an analog clock face, which are known to rotate clockwise, hence the name, the assumed direction of rotation is counterclockwise. Things counterclockwise of the high voltage reference lead it. Things clockwise of the high voltage reference lag it. For example, the YN-YN0 transformer we examined earlier has no phase shift between the high voltage and low voltage side, so the high voltage hand points straight up, and the low voltage hand also points straight up, i.e. a 0-degree differential between the high voltage and low voltage side. Conversely, the high voltage and low voltage sides of the YN/YN6 transformer we examined earlier are totally out of phase with one another, i.e. pointing in two opposite directions. So the high voltage hand points straight up. Again, the high voltage is always the reference. It always appears at the top, whereas the low voltage hand points straight down, as would an old school analog clock indicating 6 o'clock, i.e. the opposite side of the clock from 12. If you divide a 360-degree circle into 12 parts, as would an analog clock, you effectively get 30-degree shifts per position. Where 1 o'clock indicates the low voltage side lags the high voltage side by 30 degrees, 11 o'clock indicates the low voltage side leads the high voltage side by 30 degrees, 2 o'clock indicates the low voltage side lags the high voltage side by 60 degrees, 10 o'clock indicates the low voltage side leads the high voltage side by 60 degrees, and so on. While we're discussing simplified connection diagrams, phasor diagrams, and clock faces in front of us, it's probably a good idea to introduce displacement diagrams as well. You recall phasor diagrams use a circle with 0 degrees on the right-hand side and rotate counterclockwise, such that waveforms situated counterclockwise of a given reference waveform are said to lead, whereas waveforms situated clockwise of a given reference waveform are said to lag. You'd think everyone would use the same format as phasors, but they don't. Clock and displacement diagrams still stick with a counterclockwise direction of rotation and the same definitions for leading and lagging, but rather than starting out the 0-degree circle out on the right-hand side, they locate 0 degrees up the top. It isn't too big of a deal since all you're doing is effectively rotating a regular phasor diagram 90 degrees counterclockwise, but it's still annoying for those that vainly seek consistency and sense in our upside-down world. Consider the phasor and displacement diagrams for a YN/YN0 transformer. The phasor diagram for the high voltage side shows all three line to neutral phases, the reference phase 1 in black pointed at 0 degrees on the right-hand side. The high voltage displacement diagram, since it's the reference, just rotates this 90 degrees with a reference phase indicated as an arrow pointed straight up. Since the low voltage side of a YN/YN0 configured three-phase AC transformer is perfectly in phase with the high voltage side, the low voltage side phasor and displacement diagrams are essential repeats of the high voltage side, i.e. the reference phase pointing at 0 degrees on the right-hand side of the phasor diagram, and the reference phase indicated as an arrow pointed straight up and down at the top of the displacement diagram. Like I said, the displacement diagram is essentially a phasor diagram, only rotated 90 degrees counterclockwise. In contrast, the phasor and displacement diagrams for a YN/YN6 transformer look like this. Since it's the reference, the high voltage side still features a displacement diagram with reference phase 1 illustrated as an arrow pointed straight up. However, since the low voltage side of a YN/YN6 configured three-phase transformer is perfectly out of phase with the high voltage side, the low voltage side displacement diagram looks like the phasor diagram where the reference phase 1 illustrated as an arrow pointed straight down, i.e. at 6 o'clock. Again, displacement diagrams are essentially just reoriented phasor diagrams. Displacement diagrams for delta configurations, which we'll examine in a moment, use slightly different but a related notation. Consider a DD0 transformer. This nomenclature implies the high voltage side is a delta, as is the low voltage side, and there exists no phase shift between the high voltage and low voltage side. The high voltage side would be illustrated as a triangle, which is essentially the repositioned phasors for the line-to-line voltages stuck end-to-end, with an arrow indicating the reference line to neutral voltage, even though that neutral may be virtual in nature. For a DD0 transformer, both displacement diagram arrows point straight up because there's no phase shift between the high voltage and low voltage side. Conversely, for a DD6 transformer, the displacement diagram for the high voltage side points straight up, and the displacement diagram for the low voltage side points straight down. You dig? Now that we've got a quick introduction to simplified connection diagrams, displacement diagrams, and clock notation, let's see if we can interpret a couple different representative examples of three-phase transformers and call it a day. Consider a YN/D1 configured three-phase transformer. Let's first dissect the naming convention. The high voltage side is a Y with a neutral. The low voltage side is delta configured, and 1 o'clock means the low voltage side lags the high voltage side by 30 degrees. Now let's draw the displacement diagrams. The high voltage side is Y configured. It's the reference. Draw it as you would a regular Y-configured phasor diagram, only point it straight up. The low voltage side is delta configured. The low voltage side line to virtual neutral lags the high voltage side by 30 degrees. Draw it as a triangle so the reference line to virtual neutral voltage tilts at 30 degrees, kind of where 1 o'clock appears on an analog clock. Let's take a look at the simplified connection diagram for a YN-D1 configured three-phase transformer. Now don't stress out too much about drawing simplified connection diagrams from scratch, since only the meanest instructor in the world would ever make you do this. Wait a minute, let me pause the recording for a second and cackle maniacally, as would Dr. Doom when he turned Wolverine into a vegan. Anyways, don't stress out too much about drawing a simplified connection diagram from scratch, because again, only the most sadistic of instructors would make you do that. But do stress out about the proper interpretation of an already constructed simplified connection diagram. Most of the time, you'll have a simplified connection diagram on the transformer nameplate available, and it's up to you to hook it up exactly as illustrated with 0 points being awarded for creativity. This being said, it is a worthy exercise to consider how phase shift occurs between one side of a transformer and the other. The simplified connection diagram for the Y-configured high voltage side looks exactly like you'd expect, where the non-dotted ends of the 3 high voltage windings are tied together to form the central neutral connected node of a Y. The simplified connection diagram for the delta configured low voltage side necessitates some explanation. Whereas the Y connections tie together the similar ends, i.e. all dots or all no dots, delta connections tie together the dissimilar ends in a continuous ring, and then the line-to-line voltages appear at the connection points. A YN-D1 configuration looks like this: A no dot to B dot, B no dot to C dot, C no dot back to A dot, A to B to C back to A. If we were to expand this out as you would for some eye-pleasing schematic, the YN configured high voltage side would look like this, with all non-dotted ends tied together, and the delta configured low voltage side would look like this: A no dot to B dot, B no dot to C dot, C no dot back to A dot, with lower winding lowercase a between lines 1 and 2, lowercase b between lines 2 and 3, and lowercase c between lines 3 and 1. Let's say we're again making use of light industrial 120 volt line to neutral, 208 volt line to line, 60 Hz 3-phase AC, and a transformer with a 1-to-1 turns ratio. High voltage winding capital A gets mapped to low voltage winding lowercase a with no phase shift, such that the line-to-line voltage between line 1 and 2 on the low voltage side would be 120 volts at an angle of 0 degrees. Similarly, high voltage winding capital B gets mapped to low voltage winding lowercase b with no phase shift. Thus, the line-to-line voltage between line 2 and 3 on the low voltage side would be 120 volts at an angle of negative 120 degrees. Finally, high voltage winding capital C gets mapped to low voltage winding lowercase c with no phase shift. Thus, the line-to-line voltage between lines 3 and 1 on the low voltage side would be 120 volts at an angle of 120 degrees. Note my dramatic overemphasis of the term line-to-line. A YN-D1 configured transformer is effectively taking the line-to-neutral values of the high voltage Y and making them the line-to-line voltages of the low voltage delta. Those with an intimate understanding of three-phase AC and phasor math will immediately spot why the 30-degree phase shift occurs between the Y-configured high voltage side and the delta-configured low voltage side. For those failing to spot this connection, allow me to illustrate by the way of magic, or more appropriately, mathemagic. You'll no doubt recall there are 2 different styles of voltage in three-phase AC systems: line to neutral and line to line. For the Y-configured high voltage side, each winding experiences the comparatively smaller line-to-neutral voltage of 120 volts with a respective phase shift of 120 degrees between each phase. If we wanted to, we could also calculate the line-to-line voltages of the high voltage side. We perform the following calculations. Line 1 with reference to line 2 is 120 volts minus 120 volts at an angle of negative 120 degrees, which yields roughly 208 volts at an angle of 30 degrees in Brown. Similarly, line 2 with reference to line 3 is 120 volts at an angle of negative 120 minus 120 volts at an angle of 120, which yields roughly 208 volts at an angle of negative 90 degrees in orange. Finally, line 3 with reference to line 1 is 120 volts at an angle of 120 minus 120 volts at an angle of 0, which yields roughly 208 volts at an angle of 150 degrees. If you wanted to, you could reposition the line-to-line voltages on another phasor diagram so they all point from a common origin like this. However, for today's purposes, it's probably better to stick with our original diagram, simultaneously illustrating line to neutrals and line-to-line voltages. The phasor diagram clearly illustrates our reference line to neutral voltage arrow in black. We'll be pointing right here. Viewers will note the line-to-line voltages are square root 3, or roughly 1.73 times the line to neutral voltages, and still exhibit a relative phase shift of 120 degrees between each other. Viewers will additionally note the line-to-line voltages lead the nearest line to neutral voltages by 30 degrees. Make note of this fact because we're going to be using it in reverse on the low voltage side. Speaking of the low voltage side, let's do the same thing for the low voltage side. Given we're using a transformer with a 1-to-1 turns ratio, low voltage winding lowercase a between lines 1 and 2 experiences 120 volts at an angle of 0 degrees. Winding lowercase b between lines 2 and 3 experiences 120 volts at an angle of negative 120 degrees. A winding lowercase c between lines 3 and 1 experiences 120 volts at an angle of 120 degrees. Interestingly enough, these aren't line to neutral voltages anymore, but rather the line to line values given the delta configuration. Can you dig this on every level that I do? Again, a YND1 configured transformer is effectively taking the line to neutral values of the high voltage Y and making them the line to line voltages of the low voltage delta. If we use a transformer with something other than a 1-to-1 turns ratio, we could also step them up or down. However, for today's purposes, it's probably just best to illustrate the consequences of phase shifting only, something you may not be familiar with yet, rather than rehashing magnitude change, something you're probably sick of by now. To determine this new configuration's line to virtual neutrals, these little guys on the inside for the delta configured output, one could perform the reverse calculation of our previous procedure. If the line-to-line voltages are roughly 1.73 times that of line to neutrals and lead the line to neutrals by 30, it stands to conjecture that the line to neutrals are 1 over square root 3, or 1 over 1.73, or roughly 0.577 times the line to lines, and they lag the line to lines by 30 degrees. Doing so yields roughly 70 volts at an angle of negative 30 degrees, 70 volts at negative 150 degrees, and 70 volts at 90 degrees. Check it out. The reference line to virtual neutral for the delta configured output lags by 30 degrees, hence the 1 o'clock designation. All right, let's try this whole exercise again, this time making use of a YND11 configured three-phase transformer. Let's first dissect the naming convention. The high voltage side is Y configured with a neutral. The low voltage side is delta configured. 11 o'clock means the low voltage side leads the high voltage side by 30 degrees. This is kind of a repeat of the last example, only now the low voltage side leads the high voltage side by 30 degrees rather than lagging it. You should find some similarities between this and the last example, and important differences. Let's now draw the displacement diagrams. The high voltage side is Y configured. It's the reference. Draw it as you would a regular Y configured phasor diagram, only point it straight up. The low voltage side is delta configured. The low voltage side line to virtual neutral leads the high voltage side by 30 degrees. Draw it as a triangle so the reference line to virtual neutral voltage tilts at 30 degrees, kind of where 11 o'clock appears on an analog clock. Let's take a look at the simplified connection diagram for a YND11 configured three-phase transformer. The simplified connection diagram for the Y-configured high-voltage side again looks exactly like you'd expect, where the non-dotted ends of 3 high-voltage windings are tied together to form the central neutral connected node of a Y. This is identical to the high-voltage input of our previous YND1 example. Let's now take a look at the simplified connection diagram for the delta-configured low-voltage side. As with all delta connections, it still ties the dissimilar ends together, dots to no dots in a continuous ring, only this time it does so in reverse order. This is what induces the 11 o'clock or 30 degrees leading shift as opposed to the 1 o'clock or 30 degree lagging shift of the previous YND1 example. A no dot to C dot, C no dot to B dot, B no dot back to A dot. As previously, if we were to expand this out as you would for some eye-pleasing schematic, the YN configured high voltage side would look like this, with all no dotted ends tied together, and the delta configured low voltage side would look like this, A to C to B. You recall the previously examined YND1 transformer went A to B to C. Let's see how the reversal affects low voltage secondary output for a YND11 transformer. As previously, high voltage winding capital A gets mapped to low voltage winding lowercase a with no phase shift. Where's winding lowercase a now? It's between 3 and 1 this time, only it's being used backwards. Similar observations can be made about windings b and c. Lowercase b is between 1 and 2, backwards, and lowercase c is between 2 and 3, also backwards. Dig what's going on in this configuration? Line-to-line voltage from 1 to 2 is the inverse of b. Line-to-line voltage from 2 to 3 is the inverse of c, and line-to-line voltage from 3 to 1 is the inverse of a. Cunning indeed. Given we're using a transformer with a 1-to-1 turns ratio, line-to-line voltage from 1 to 2 is the inverse of b, or 120 volts at an angle of 60 degrees. Line-to-line voltage from 2 to 3 is the inverse of c, or 120 volts at an angle of negative 60 degrees. And line-to-line voltage from 3 back to 1 is the inverse of a, or 120 volts at an angle of positive or negative 180. When you assemble these phasors end to end as you would a delta, it looks like the low voltage secondary output voltage reference to virtual neutral is tilted 30 degrees in advance, i.e. at 11 o'clock of the primary high voltage inputs, as you'd expect for a YND11 configuration. As a means of verifying this, we can calculate the line to virtual neutral values given the understanding that line to virtual neutrals are 1 over square root 3 or 1 over 1.73 or roughly 0.577 times the line to lines and lag the lines to lines by 30 degrees. Doing so yields roughly 70 volts at an angle of 30 degrees, 70 volts at an angle of negative 90 degrees, and 70 volts at 150 degrees. Check it out. The reference line to virtual neutral voltage for the delta configured output leads by 30 degrees, hence the 11 o'clock designation. All right, now that you're warming up to this nonsense, let's try a couple more illustrated examples at a higher rate of speed. Consider DD0 configured three-phase transformers. All I want you to do is interpret the information given your understanding of three-phase transformer nomenclature, simplified connection diagrams, and displacement diagrams. Let's begin our analysis by dissecting the name convention. The high voltage side is delta configured. The low voltage side is also delta configured, and 0 o'clock means the low voltage side is perfectly in phase with the high voltage side. Let's now draw the displacement diagrams. The high voltage side is delta configured, so one will draw it as a triangle with a reference line to virtual neutral voltage pointing straight up. The low voltage side is also delta configured, so one would also draw as a triangle with a reference line to virtual neutral voltage pointed straight up. As we might expect, for a DD0 with no phase shift between the high voltage and low voltage side, the simplified connection diagram for both the high voltage and low voltage delta configured sides are identical to each other. A node dot to B dot, B node dot to C dot, C node dot back to A to B to C back to A. As with the identical simplified connection diagrams, the phasor diagrams for the high voltage and low voltage sides are perfect copies of one another, so as the resultant line-to-line voltage outputs are perfectly in phase with the applied line-to-line voltage inputs. Similarly, the resultant line to neutrals for both sides are in phase with one another. Example 4, let's do this in reverse. What if we flip-flop the low voltage side for the simplified connection diagram? Understandably, this would be a DD6 configuration. The high voltage side is delta configured. The low voltage side is also delta configured. 6 o'clock means the low voltage side is perfectly out of phase with the high voltage side. As we demonstrated earlier, the high voltage side would be drawn as a triangle with a reference line to virtual neutral voltage pointing straight up. The low voltage side will also be drawn as a triangle with a reference line to virtual neutral voltage pointing straight down. The simplified connection diagram for the high voltage side of a DD6 transformer indicates a standard delta connection. Winding capital A is between lines 1 and 2, winding capital B is between lines 2 and 3, and winding capital C is between lines 3 and 1. As you might expect, the simplified connection diagram for the low voltage side indicates the low voltage windings are simply being used in reverse. Winding lowercase a is still between lines 1 and 2, only it's being run in reverse. Similarly, winding lowercase b is still between lines 2 and 3, only it's being run in reverse. And finally, winding lowercase c is still between lines 3 and 1, only it's being run in reverse. As you might expect, the phasor diagrams of the high voltage and low voltage sides are opposite of one another, such the resultant line-to-line voltage outputs are perfectly out of phase with the applied line-to-line voltage inputs. Similarly, the resultant line to neutrals for both sides are perfectly out of phase with one another. All right, those last two were pretty easy. Consider DYN11 configured three-phase transformer with a 1-to-1 turns ratio being supplied by a 277 volt line to neutral, 480 volt line to line, 60 Hz three-phase AC system. Since I simply can't resist the temptation to perform a detailed phasor analysis of this system, let's all get on the same page. Given a delta configured input uses 3 wires and lacks a neutral, it'd ordinarily be foolish of us to use line to neutral values as our reference, but that option is available to us if it makes our work easier, and in this case it does. For this reason, let's consider line 1 to neutral to be 277 volts at an angle of 0 degrees, line 2 to neutral to be 277 volts at an angle of negative 120, and line 3 to neutral to be 277 volts at an angle of 120 degrees. Thus, line 1 to 2 would be 480 volts at an angle of 30 degrees, line 2 to 3 would be 480 volts at an angle of negative 90 degrees, and line 3 to 1 would be 480 volts at an angle of 150 degrees. As you might expect, the line-to-line values are roughly 1.73 times that of the line-to-neutral values and lead the nearest line to neutrals by 30 degrees. Let's begin our analysis by dissecting the naming convention. The high voltage side is delta configured. The low voltage side is Y configured with a neutral. The low voltage side leads the high voltage side by 30 degrees. Let's now draw the displacement diagram. The high voltage side is delta configured, so you draw it as a triangle with a reference line to the virtual neutral voltage pointing straight up. This is the reason I made the air characteristic decision to employ the line to neutrals as the reference, even though we're making use of a 3-wire delta configuration. Given an 11 o'clock designation, the Y-configured low-voltage side's line to neutral leads the high-voltage side's line to virtual neutral by 30 degrees. You draw this as a regular Y-configured phasor diagram, only tilted at 11 o'clock or positive 30 degrees. We've got this example still in front of us. The simplified connection diagram for a DYN11 configured 3-phase transformer might look something like this. The delta configured primary shows a continuous connection from A node dot to B dot, B node dot to C dot, C node dot back to A dot. Line-to-line voltage 1 to 2 at 480 volts at an angle of 30 degrees is applied to the high voltage primary winding capital A. Line-to-line voltage 2 to 3 at 480 volts at an angle of negative 90 degrees is applied to high voltage primary winding at capital B. And finally, line-to-line voltage from 3 to 1 at 480 volts at 150 degrees is applied to high voltage primary winding capital C. The Y-configured primary ties together all the non-dotted terminals at an accessible neutral. As with all scenarios, primary high voltage winding capital A maps directly to secondary low voltage winding lowercase a with no phase shift, capital B to lowercase b, and capital C to lowercase c. This configuration is effectively transforming the line-to-line voltages at the high voltage primary into line-to-neutral voltages at the low voltage secondary. Given a transformer with a 1-to-1 turns ratio, the low voltage secondary experiences 480 volts at an angle of 30 degrees on low voltage winding lowercase a, 480 volts at an angle of negative 90 degrees on low voltage winding lowercase b, and 480 volts at an angle of 150 degrees on low voltage winding lowercase c. This quickly and directly demonstrates the reference line to neutral voltage at the secondary output leads the high voltage input by 30 degrees, thus the 11 o'clock designation. While it's not necessary to do so, while this example is still in front of us, if we wanted to, we could calculate the resultant line-to-line voltages at the secondary, with the understanding that they'll be roughly 1.73 times that of the line-to-neutral voltages, and lead them by 30 degrees. Line 1 with reference to 2, at the low voltage secondary, will have a value of roughly 832 volts at an angle of 60 degrees. Line 2 with reference to line 3 will have a value of roughly 832 volts at an angle of negative 60 degrees. And line 3 with reference to line 1 will have a value of roughly 832 volts at an angle of positive or negative 180. This goes to show you, even though you're using a 1-to-1 transformer, and even though this is called the low voltage side, connection can influence phase shifts such that resultant voltages are substantially amplified. All right, let's try another example, only this time let's go in an opposite direction. Consider a 3-phase transformer with a 20-to-1 turns ratio, designed to step down 220 kilovolts to 11 kilovolts with the following simplified connection diagram, and we know the low voltage secondary side lags the high voltage primary side by 30 degrees. Can you form the nomenclature and draw the displacement diagram given the information you have in front of you? Let's do the easy part first. The clock notation for a transformer with a low voltage secondary side that lags the high voltage primary side by 30 degrees is clearly in the 1 o'clock group. Let's take a look at the simplified connection diagram to make sense of the primary and secondary configurations. The high voltage primary seems to be a continuous chain. A node dot to C dot, C node dot to B dot, B node dot back to A dot. We're clearly dealing with a delta configured primary. This being said, it's a little different from the DYN11 we just looked at, since we're now going from A to C to B, rather than A to B to C. Line-to-line voltage 1 to 2 is applied to inverted winding B. Line-to-line voltage 2 to 3 is applied to winding C inverted. And finally, line-to-line voltage 3 to 1 is applied to inverted winding A. Long story short, the high voltage side is a delta, so you get a capital D. The low voltage secondary appears to tie together all the non-polarity ends of the three windings and bring this out as a fourth neutral wire. Understandably, this is a Y-configured low voltage secondary with a neutral, so you got lowercase yn. Thus, the nomenclature would indicate that this is a DYN1 transformer. The displacement diagram would illustrate the high voltage delta as a triangle pointed straight up and down, and the low voltage secondary is a Y tilted 30 degrees to the right. All right, try this last example problem on for size, which might not be as easy as you think. Consider a transformer with a 1 to 20 turns ratio designed to step up 11 kilovolts to 220 kilovolts with a Y-configured low voltage primary and a delta-configured high voltage secondary, where the high voltage output leads the low voltage input by 30 degrees. Now, before you rush off and screw this up, let me tell you something up front. The answer is not YND11. Pay attention to the dramatic emphasis I'm placing on certain terms. I say again, consider a step-up transformer with a Y-configured low voltage primary input and a delta-configured high voltage secondary output, where the high voltage output leads the low voltage input by 30 degrees. Let me remind you that the standard nomenclature format indicates the high voltage side first in capital letters, the low voltage side second in lowercase letters, and the phase shift of the low voltage with respect to the high voltage side using clock notation. For a majority of these examples, we've been assuming a high voltage primary to low voltage secondary step down transformer. Here we're clearly dealing with something not matching that previous format. It's a step-up transformer. What's the primary input for a step-up? Low voltage or high voltage? What's the secondary output for a step-up? Low voltage or high voltage? Aha! Additionally, what does the standard nomenclature assume to be the reference when considering phase shift? High voltage or low voltage? If we were to use standard nomenclature, which we are going to, we need to express the delta-configured high voltage secondary output side first as capital D. The Y-configured low voltage primary input side with the neutral second using lowercase yn, and then reference low voltage input with respect to high voltage output, not the other way around. If high voltage output leads low voltage input by 30 degrees, this is the same thing as saying low voltage input lags high voltage output by 30 degrees. We're clearly dealing with a 1 o'clock transformer. Thus, this 1 to 20 step-up transformer is also a DYN1. The exact same designation as our previous example, only it's being run in reverse. Does this or does this not make sense? If you've been paying attention to the standard nomenclature format, it does make sense, because transformers are bidirectional in nature. A 20 to 1 step-down transformer with a delta-configured high-voltage primary input and a Y-configured low-voltage secondary output, where low-voltage output lags high-voltage input by 30 degrees, i.e. a DYN1, is a 1 to 20 step-up transformer with a Y-configured low-voltage primary input and a delta-configured high-voltage secondary output, where high-voltage output leads low-voltage input by 30 degrees, i.e. also a DYN1, for one important reason, that reason being the terms primary input and secondary output are dependent upon application, whereas the terms high voltage and low voltage are not. I would suggest taking a moment to cool your brain after that one. If you survive this last example problem with your dignity still intact, you do indeed understand standard three-phase AC transformer nomenclature format. Now, some of you might be worried that this lecture is just about wrapping up and I haven't gone over all 16 recognized arrangements of regular Y and delta configurations in exhausting detail, let alone the additional recognized 10 zigzag bonus configurations. The reason I placed a lot of emphasis on the 0, 1, 11, and 6 groups in the examples is because that's what you're most likely going to run across in the field, and only in the oddest of odd occasions will you ever run into their mutant cousins. And even if you do run across something like, let's say, YD5, it's undoubtedly a Y-configured high voltage side, a delta-configured low voltage side, such that the low voltage side lags the high voltage side by 5 times 30 or 150 degrees. See? Too easy. It's just 3 parts. High voltage in all caps, low voltage in lowercase, phase shift of the low voltage side with respect to the high voltage side using clock notation where each hour position represents 30 degrees. Now I know the comments are just going to be full of oh-so-polite requests in all caps awash with spelling errors like, "Sir, I demand you must now tell square root 3-phase transformer with square root 2 o'clock phase shift without using math, phasor, spelled wrong, and confusing electric. I await your response! Exclamation point." But I am leaving the rest of these rarities as examples for you to work out on your own using the tools I gave you today. Really, the intended purpose of this lecture was not to slog through the transformer dungeon and slay every goblin, giant spider, gelatinous cube, and dragon in it, but rather to simply introduce transformer nomenclature, displacement diagrams, and simplified connection diagrams on an introductory level. Again, in ordinary circumstances, most of the time you'll have a simplified connection diagram on the transformer nameplate available, and it's up to you to interpret it properly and hook it up exactly as illustrated, with 0 points being awarded for creativity. Maybe if I've got time, which I won't, so don't hold your breath, I'll publish some short videos featuring specific examples of 3-phase AC transformer configurations in greater detail. This being said, I should at least briefly describe a zigzag or a Z connection before bringing this lecture to a close. Zigzags are kind of like Ys, or if you're an idiot, stars. Only they have double the number of windings for each phase shift, such that if you're super desperate for a super weird phase shift or an odd voltage magnitude, or you just want to confuse somebody, you can use part of one winding from one phase and part of another winding from another phase to create the desired phase shift and or magnitude. Since this is difficult to describe verbally, it's perhaps worthy of one more illustrated example. Let's take a look at a random configuration like YZ11. At least the nomenclature is easy enough to interpret now that you know how it works. The high voltage side is Y configured. The low voltage side uses a zigzag connection, which I'll explain in a moment, and the low voltage side leads the high voltage side by 30 degrees. The high voltage side is configured like a standard Y, with the non-dotted terminals forming the central node of a Y. Too easy. Now comes the hard part. The low voltage side using a zigzag connection has 2 windings per phase, for a total of 6. High voltage winding capital A maps to both low voltage windings, lowercase a1 and a3. Similarly, high voltage winding capital B maps to both low voltage windings, lowercase b1 and b3. And finally, high voltage winding capital C maps to both low voltage windings, lowercase c1 and c3. For the sake of argument, let's say both the low voltage windings have 1:1 turns ratio with a high voltage input, such that if we're making use of light industrial 60 Hz 3-phase AC characterized by 120 volts line to neutral, 208 volts line to line, both A1 and A3 would be 120 volts at an angle of 0 degrees. Both B1 and B3 would be 120 volts at an angle of negative 120 degrees. And finally, both C1 and C3 would be 120 volts at an angle of 120 degrees. I found one way of effectively illustrating the result of a zigzag connection is to first draw the phasors for each low voltage winding independently rather than grouping them on one diagram. I should additionally remind you that not everything you see on the internet is true. Case in point, there are startlingly incorrect depictions of zigzag connected transformers floating around out there that sometimes appear in otherwise reputable trade magazines and textbooks. Be warned. A properly configured YZ11 connection ties together the dotted ends of A3, B3, and C3. Not the non-dotted ends, the dotted ends. And then rather sticking with their respective phases, the non-dotted end of B3 is joined to the non-dotted end of A1. The non-dotted end of C3 is joined to the non-dotted end of B1. And finally, the non-dotted end of A3 is joined to the non-dotted end of C1. This is where it's helpful to have drawn the 6 low voltage phasors independently. Since we're using the coils A3, B3, and C3 inverted, we can draw these inverted phasors as well. The inversion of A3 is 120 volts at an angle of 180. The inversion of B3 is 120 volts at an angle of 60 degrees. And the inversion of C3 is 120 volts at an angle of negative 60 degrees. Now, just join the appropriate phasors head to tail. Line 1 with respect to the neutral is inverted B3 plus A1, or 208 volts at an angle of 30 degrees. Line 2 with respect to neutral is inverted C3 plus B1, or 208 volts at an angle of negative 90. And finally, line 3 with respect to neutral is inverted A3 plus C1, or 208 volts at an angle of 150. If you want to think of it this way, a zigzag is kind of like a Y with bent arms. In this case, the low voltage side reference phase to neutral voltage is clearly leading the high voltage side by 30 degrees, as you'd expect for an 11 o'clock transformer. All right, before we bring this lecture to a close, let me at least attempt to partially answer an important question about three-phase transformers that might be burning in the back of your mind. That question is this: why? Why are we doing this? Why are we going from delta to delta, Y to Y, Y to delta, delta to Y, and sometimes Z and back again? This question has many, many answers, ranging from the simple to the complex. On a superficial level, three-phase transformers play the exact role single-phase transformers do, which is step up or step down voltage. Using this initial perspective, we can say it makes more economical sense to generate power at low voltage than step it up to transmit it. And it's much safer to step it down at the point of use. If we were to use transformers with anything other than the 1-to-1 turns ratio that I employed for a majority of these examples, it'd be super easy to demonstrate that three-phase transformers can do this as well. This is true, but it actually goes a lot deeper than that. If we were to start expanding our perspective, in addition to stepping up and down voltage and isolating the primary and secondary voltage, a three-phase AC transformer can also change the configuration of a three-phase AC system. For example, you can change a 3-wire delta configuration to a 4-wire Y, a 3-wire Y, or vice versa. If you don't have a neutral and you need a neutral, you can create one. If you got a neutral and you want to get rid of it, you can make it disappear. Beyond adding or subtracting a wire, dependent upon application, a delta might have certain advantages over a Y, whereas in other applications, a Y configuration might have certain advantages over a delta. Certain transformer configurations aren't as susceptible to electrical harmonics, which are like additional higher frequency sinusoidal waveforms superimposed on the fundamental frequency. Additionally, as we'll learn in later lectures on symmetric component analysis and protective relays, a fault on one side of a transformer when configured in a certain fashion might get trapped on one side of the transformer, thereby offering a degree of robustness to the larger generation, collection, transmission, and distribution system. Finally, if we were to fully expand our perspective about the purpose of three-phase transformers, it really is all about phase shift. As we'll learn in later lectures on AC transmission, power lines are not the idealized zero-ohm unreactive conduits you may think they are, and at risk of oversimplifying it, it often necessitates a phase shift from one end to another to push power to its intended direction. Lest you think that phase shift is only important to AC applications, phase shift has other important applications inside high-voltage DC transmission, which is essentially the large-scale rectification of AC to DC, transmittal over long distances, and then the subsequent inversion of DC back to AC at the point of use. Given ordinary rectified three-phase AC on the DC link, there's a noticeable ripple, which may cause unwanted harmonics. However, rectifying the original unshifted AC along with the output of a Y to delta transformer with a 30-degree phase shift, it noticeably smooths out the rectified result such that much less ripple is observed and resultant harmonics reduced. We'll examine this and many other applications of three-phase transformers in later lectures. Until then, that's it for now. In conclusion, this lecture examined three-phase transformers, electrical devices used to step up, step down, isolate, change the electrical configuration, and phase shift three-phase AC voltage. We additionally learned to interpret standard three-phase AC transformer nomenclature and simplified connection and displacement diagrams, and took a look at a handful of representative examples. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.